break it up into three different parts, where I first describe the encoder, where I put two linear layers to then decompose the mean and the sigma. I then I also made a separate decoder, which just takes in the lane variable. Well, I guess let me go line by line. So to properly encode our data, we are starting from our high dimensional. In this case, I'm using the MNIST data set, so it's a 28 pixel by 28 pixel image, and then I just chose, I think I divided by 2 each time. You don't necessarily need to do this. It's just the idea that these linear layers should be descending. So such that it can begin to compress your data. And then it's important as well to have to decompose your output into these individual components, because having just the latent variable output won't be helpful in the long run. So to reiterate what I said, the encoder outputs the latent vector z, and then we decompose these into mu and I do log variance just to make sure that our variance is greater than 0. Then the decoder, is just in terms of architecture is the opposite of the encoder. So I just had it scale back up by the same linear layers as the encoder, back up to a 28 by 28 image. And then I call both of these classes within the VAE, and this is where the entirety of the model happens. So specifically what I mean is we get our mu and variance from the encoder. We then check to see if the encoder, if the VAE is going through training, and if it does, we go through the reparam trick, which I guess reminds me that we didn't really cover that as much. So I think, as a quick step back, it's important to describe, at least high level, what the reparam trick is actually doing. So within the reparam trick, which is really described by epsilon, we are doing the equivalent of, well, I guess the purpose of the reparam trick is such that we have built a Gaussian using mean and variance, and then sampling from that Gaussian to then be the input into the decoder. But to backpropagate through this randomly sampled Gaussian is impossible to do. So as a way to fix this issue, we use this this kind of like a I don't know what word to use. I guess you can think of it as like it's a Gaussian distribution with mean 0 and variance 1. But I think at a high level idea, a way to think of it is the equivalent of multiplying our sampled values from mu and sigma by 1. So what does that mean? So we take this our mu and sigma, which we have sampled. So let's say, just for like a example, mean is 4, and sigma is 1, you know. And we have sampled, and we sample some value from this distribution. So we now have a specific value, specific probability. What we can do is, to make sure that we can still backpropagate through this mean and variance, we instead make, instead of sampling straight from the mean and variance, what we can do is we take the values of 4 and 1, 4 being the mean, variance being 1 being the variance, and we multiply that by this other Gaussian of mean 0 and variance 1. So what that looks like is we multiply it. I should say multiply this epsilon Gaussian by the variance, or in this case, its standard deviation, and then we add the mean. So we are effectively making this kind of fake Gaussian that looks exactly like what is described by just mu and sigma. So that way mu and sigma are untouched, and we can backpropagate through them, but we can also get the sampling from this epsilon Gaussian. So this is kind of like the high-level idea of the reparam trick. And we only use this during backpropagation. So in the code, we check to see if we are training, and thus, doing backpropagation. And if we are, we use the reparam trick. And if not, then fine. I guess this is actually an error. The z should be both mu and variance, right? But we then have this lane variable put into the decoder, and the decoder outputs the reconstructed x hat. So as I kind of described earlier, this is then used to be put into our elbow loss. And like I said earlier as well, the elbow loss is comprised of the log likelihood and the KL divergence, which... yeah, go ahead.
Your forward pass for the decoder, I see, like, if you're not training, you essentially just throw away the log variance.
Yeah, I just said that this is a bug. Like, I should be describing when in the event where we're not just training, that it should. I don't know why I left this out. The log variance.
Right. So what should it be?
It should be plus the log variance. So yeah, I mean, I guess that's really it. I kind of explained the
why plus log variance?
Because that would describe the Gaussian.
And Gaussian isn't just the addition of two vectors.
Yeah, I might have a misunderstanding then.
Yeah, I mean, this is like, well, I don't see why, like, you need to have different behavior in the forward pass for training tests. Essentially, I think you should always do, like, whatever your reparameterized function does.
I think it depends. This might be some sort of, like, cargo code programming. So, like,
happy with how
Yeah. Did you code this yourself? Like, did you find some other VAE implementation and just kind of adapted it?
No, I coded this myself.
I see. So the reason why I asked that it's quite common in VAEs to treat the mu as the latent encoding. So I think in your diagram you kind of like had this erroneous thing where you had the latent space here, right? But if you just wanted to extract features, right, to use the encoder as a feature extractor, then the most common way of doing this is by just taking the mean. And most VAE implementations, in fact, do this. So, if you had adapted your code from someone, then that's probably what they were doing.
How would that make sense?
This is the.
Sorry?
How would it make sense to just take, the mean? Because, like, I don't know.
In fact, that's the point of with highest probability according to your distribution. So it seems like a pretty good choice to pick if you had to pick a single representation.
I mean, not necessarily, right?
In what sense?
Like, just because it has the highest probability, is the highest probability latent, doesn't mean it's the highest probability decoding.
Just because the highest probability. Oh no, sure, yeah. I mean, it's quite. I mean, I think in fact in practice, like if you do this, it's not a good thing, right? Like the kind of outputs you get are not very good. But if you just care about feature extraction, then it's probably the only sensible choice.
Yeah.
Well, it's the only deterministic choice.
Yeah.
Okay, I didn't know that. Yeah, I know that there's a lot of holes in my